Hello, my friends. Welcome back. We're here again. End of the first week almost, which is absolutely incredible.
So you can get them recorded, and then like the
Bit of news on the homework, the binary basics. Don't do problem 5. So scratch number 5, please. Not a good problem. I was looking at, I was like, let's just not do it. I got something that'll get us to the same understanding. We'll just talk about it today. What I thought we would do today is I want to talk a little bit more about the precision of computers, a single precision and a double precision machine. How fine is the resolution of real numbers? We know it's not all of them. And then, let's see, what else did I want to talk about? I wanted to talk a little bit about how do computers add? How do you actually use logic, pure logic, to add? That's just freaking awesome. I was going to talk about how memory works, but I don't know that I can explain it well. Let's see, Josephine, you were talking about SR latches and flip-flops and stuff. Who all has seen flip-flops and SR latches? And I know you have. So I'm not going to talk about that. It's like I can't even explain it to myself. It's cool, but I can't explain it to myself. And then I wanted to show you the origami thing that I wanted to tell you about, how to do binary conversions using paper and folding. Super simple, pretty easy. This group will get it. I was thinking you were at you were both at the scholarship activity that I did this for. Is anyone else? You were also, Ms. Libby. And
I think I was.
Were you too, Eva?
Yeah.
Yeah.
I remember I did something with folding. Was it like 3 years ago? Or
I mean, we did do that, I think, last year
I don't know if we got to
also.
the conversion.
I think we did it on like Zoom during
Oh,
COVID.
that's
Yeah, this will be in person. It's like a whole other thing.
that's the one I did.
Okay.
And then I wanted to just give you a little time to work on some stuff while we're all here together. We don't meet on Monday, so I thought it'd be nice if you have any questions, or maybe you could start forming questions because you would be beginning the assignment. And so that's cool too. I get it. It's all good. So before I start, do y'all have any questions or anything? Let's see, Josephine, I gotta move over here. Hi.
When's your office hours?
They are right after, they are 11 to 2. I teach at 2, so head it out right before then. Monday, Wednesday, and then 1 to 2 on Friday.
Okay.
Or by appointment, if you need to meet, we can do it other times. Probably be Zoom, but anything else? Groovy. All right. So I have a problem for you. I actually would like you to do something for me. Find the IEEE, oh yeah, that's right, 754, like there's another one, form of 1 in base 10. Just what does a 1 look like in IEEE format? Let's just take a minute to do that, please. There's a point to this, it's not just busy work. Without using a converter. We can check ourselves with the converters, but we don't want to. That's okay. Some of you probably don't have this down, and that's totally cool. We're here to talk about it. Let's see if I can find my circuit model. And we wanted, sorry, single precision is also what we want to do. Just a hint of what you want to do. You want to write this as something times 2 to a power. That's your first step for IEEE. You want this to be a number that leads with 1. Probably can figure out what the rest should be based on that. Make it a little tinier. So that's what you got to fill in. And then you got to fill in that. Let's just start there and talk it through. It's weird to think in the binary scientific notation, exponential notation. So this thought it'd be cool to warm up with a little bit. And last time, just another thing, you want to, I think I said add 128, that was off by 1. You want to add 127 to the desired exponent. I think I said 128, that is wrong. Can they help me here? I need help. I need help in lots of ways, but a lot of them aren't appropriate for the classroom discussion. Anybody help me on this? What power of 2 do you think we want?
0.
0. Yeah, we want it to be 1, so 0 is the power. What number needs to go in front? So that's times 1. Now, if I've got a 0 there, so this has to be the actual number I'm representing.
1.
So just 1.00, exactly. So step 1 is to notice that 1 in base 10 can be written in base 2. Now this is base 2. I'm going to put a bunch of zeros here, times 2 to the 0th power. Does that make sense? Let me just stop. Let's just make sure this is resonating. Cool. Appreciate the nods. Thank you. Many thanks. Any questions on just this? I'm happy to, if you've been in class with me before, you know I'm happy to explain things all day long over and over in different ways. Okay. What goes in the sign bit? 0 or 1?
0.
0, why?
It's positive.
It's a positive. Only negatives get a 1 as the sign bit. And then my exponent, so let's just make some notes here. The sign bit equals 0. The exponent is going to equal the true exponent plus 127. So this is the desired exponent. Plus 127 in base 2. So could you just find that for me, please? What is 127 in base 2? Try the conversion thing with division by 2. Try to do it without a calculator. You might even just know it because you're a computer person and 127 kind of shows up a lot. I'm so happy to be here with y'all. This is really one of my favorite classes. And you're some of my favorite people. It's great. I'm so stoked when I looked at the roster, and now I'm getting to meet new cool people too. So some of y'all I've just seen in the math lobby. Like Joseph.
Column.
So remember, the conversion is just divide by 2 and record the remainder. So I'll put a little remainder column over here. So when I divide by 2, 63. Wait, is that right? Yes. Remainder 1, divide that by 2 is 31. Remainder of 1. Divide that by 2 is 15 with remainder of 1. Divide by 2, 7 R1. Divide by 2. I'm not going to keep saying that. It's getting a little much even for me. And then how many times 2 go in there? 1 time with a 1 left over. So does that look good? So one of the, yes, thank you for counting, Lavina. Yeah, this is good. Hopefully I have 7 ones there. Thank goodness. So then the thing we record is the remainders in backwards order. So I have 7 of them. I want 8 bits. So notice that I'm going to have to insert a 0 in the front, space holder for the 8th bit, and then everything else is 1s. And that's a base 2. Let me stop there. How does that feel? Cool. We're good? Yes, yes.
Why are we adding the 0 in the front?
Because I will need 8 bits. Every exponent needs 8 bits of description.
So if we don't have 8, we just add a bunch of.
You just tack them onto the front. Yeah, perfect. If this had turned out to just be, a 1, I would have to tack 7 zeros in the front. Cool, great question. Okay, so this is pretty straightforward. Now we've got, let's write this out again. So it's 1 point, bunch of zeros, base 2, times 2 to the 0.12, excuse me, just 0, 1, 2, 3, 4, 5, 6, 7, base 2. So that's 1, base 10 so far. Kind of helps to do these because sometimes you can mistake these things for base 10. It's just easier to keep the little sub 2s around for my mind anyway. All right, so I'm gonna put in this number here, these 8 bits, 0, 1, 2, 3, 4, 5, 6, 7, cool. What do I record for the mantissa-ish? Because it's not really all of that, right? What are you thinking, Lou?
Wasn't it just everything after the decimal?
Everything after the decimal. So you pull that 1 out, and the only time you wouldn't have that is if we actually were trying to encode a 0, which we'll take a look at. Josephine, do you have a question?
Can we move the projector if we're not going to use it?
We can totally, yes. What a great question. Thanks, kind of. Can I want to lay it on its side. It's kind of, what the fuck is going on here? Hold on. Oh my God. Christian, will you hold that so I don't break this? Because we're just going to run. If this thing falls, we're leaving and never coming back. Okay. Let's try that. That's something. How's that?
Thank you. Yeah.
You're welcome. Thank you. Great stuff. Yes, ma'am. I can't move that.
No, like there's
Oh,
something
it has
on its
a
notification. Yeah, I don't know if
Oh,
it's
it's
still
asking about a
recording or not.
personal hotspot.
Oh, weird. It better not have stopped.
It's still recording.
Yeah, it's
Okay.
still recording.
All right, thank you. Good, thank you. Man, together we can do this. I appreciate you all. So I got that, so I'm just gonna record zeros here. And I'm gonna record 23 of them, so I'm not gonna write that all out. I'm just gonna notice that there are 23 zeros there in a row. That's a 1. Outstanding. You can check me if you go to one of the IEEE converters I've linked to in the content area. We got it covered. So the question I want to ask you, and I'd like you to think about this for just a few minutes, what is the next number I can produce? So what is the smallest step toward the positive side that I can produce? And what I'm getting at here is a thing called the machine epsilon. And the machine epsilon, you can think of this as the smallest positive value we can represent. So what we're gonna look at, and a good way to see this, is you find the representation for one, you figure that out, and then you find the next number. So we're kind of just looking for, if we were to list out all the possible numbers this computer could represent in single precision, we know we can't get them all. What's this next one here? And that is an epsilon, in theory. So what do you think? What is the next number? And this might help here. Lou, what do you think?
Would it be like 2 to the -23rd?
It will, so the epsilon will
Yeah,
be.
that's what
Yes,
it'd be.
yeah,
I don't
exactly.
know what that would. I don't even know. Like that's really small.
Gotcha, no, that's good. That's, it's not as small as we would like. It's not like small enough to go to the moon or anything like that, I don't think. It might be, I don't know. I haven't been to the moon under my own power. So the next number up, 1 plus epsilon base 10, is just, I'm just gonna tack a 1 into that finest detail that I'm allowed. So this number here, with 22 zeros and then a 1, base 2 times 2 to the representation of 0, base 2. So that's the smallest step up I can take. And notice that this piece right here then, this is, remember how this works? This is 2 to the -1st, this is 2 to the -2nd, -3rd, 4th. So this, just as Lou said, is 2 to the -23rd. And that is the smallest number we can produce in single precision. So 1 plus epsilon is basically going to be 1 plus 2 to the -23rd. What is 2 to the -23rd? Could someone crank that out in decimal? What is that in decimal form? 2 to the -23rd is approximately what? In scientific notation base 10. You just need a calculator. I don't expect you to do this in your head, but if you do, we're going on the road. You can do this shit in your head, yeah. I don't know where we're going. I don't know who will pay to see that, but somebody will. You can add it to your shows, Christian. It's like, you'll open the show with that. Get the crowd roaring.
It's like I'm not in the middle.
Can somebody just on a calculator? Or don't make me do it. Okay.
I got 1.19 times 10 to the -7.
Love it. Thank you. Thank you, Thomas. So that is the smallest number in single precision. So the epsilon in single precision is this. That's, what is that? So it's 0.123456119. So that means in single precision, this is how accurate you can get. Anything that moves into the 7th place, you cannot trust. So here's where our full precision lies. So we have full precision to 6 decimal digits. That's okay, but not if you're a quantum physicist. I verified this with a quantum physicist. This isn't good enough. Could you now use the same reasoning to tell me what is the epsilon, what is the machine epsilon for double precision? Look at this pattern. Go back and look. Let me just put it up here as a quick refresher. Because double precision is where we live. Single precision is, you guys probably never played on an Atari 2600 video game console. You might have for retro fun. But we don't really mess with single precision anymore. Everything's double. So in double precision, let me just show you what the IEEE format is. We have, again, a sign bit. So I have one sign bit. It works the same way. What was my exponent? How many bits? 11. Wait, it's in there somewhere, right? more than 10. Just one more than 10. It was 11. It's weird. You would think it would be 16 because it's like double, but they're trying to maximize the amount of detail that we can keep here. So this is how many bits left over?
52.
52. So look at the rhythm. What is the machine epsilon for double precision? Say you didn't study for the test. Here's the test. You didn't study for it, but you're smart. You can see this rhythm. Single precision was this. What is the double precision epsilon? Yes, Josephine.
2 to the negative 52.
Indeed. Is that what you're going to say, Kyle? Sorry, I didn't see it. So, okay. 2 to the negative 52. My friends, don't make me get this faster than you on this stupid computer. But I'm going to try until someone tells me first. See, I have to log in. Like, my God, do you not have it yet? Come on, friends.
I got 2.22 times 10 to the negative 16.
Thank you, sir. And cool. So that was 2.22 times 10 to the negative 16?
Yeah.
Beautiful. Beautiful. So now, what can we really count on? So this is equal to 2, let's see, so 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 15, 2, 2, 2. So here's our resolution. Here's where we can trust things, as long as we stay in the, 15 decimal places. So we've got about 15 decimal places of accuracy. And that's enough. I checked with Dr. Gray on this. That's enough for all the physics he knows. He knows a lot. So, this is why some of the things we've been doing have been showing up wrong. When we were doing our basic math here, when we convert these things into IEEE format, we're losing details. This can't be written perfectly in binary. The only things that can be written perfectly in binary are things that involve powers of 2, but this doesn't have that at all. So each of these things has error, and depending on how we add them, that error propagates or doesn't propagate. And we're not going to study much more detail about it. I just want you to understand the nature of precision in these machines. And we're still going to be able to do calculus, and we still clearly can send ships to asteroids and amazing things like that. And it all works out good. So, let's say you've got some binary numbers. Let's just talk about how addition works really quick. Subtraction gets fun and funky. We're not going to really take a look at it. I just want you to have a feeling for these things. Binary addition. Let's say I wanted to add 1, 0, 1, 0, 1, 1. What is that? What decimal number is? These are all base 2, so everything here will be base 2. What decimal number is that?
43.
Is that, I'm gonna trust you.
I might be lying though.
What's that?
I might be lying.
Who's you, were you lying? I don't know, I'm gonna trust you. Let's see. So we've got 1, 2, 8, 32, and then none of the 16s and none of the 4s, so what do we got? 43, beautiful, nice, thank you. So that's 43, and we're going to add to it, how about just 7? So that is actually 7. Base 10, it's 1 plus 2 plus 4. So when you do addition, it's just like base 10 addition, except that the carry happens when you add up to 2. So think about how base 10 addition works. If I had 173 plus 27, and I added, this would become 2 digits. It's 10. So, and 10 is my base. So I put down the ones, I carry the tens place, and then I've got to do it again. Here I have another 10, and I carry that one, and I've got 200. So over here, the same idea is going to work. I've got 1 plus 1, but that's 2. What does 2 look like in binary? It is a 1, 0, right? So it looks like a 10, but it's not a 10, it's a 2. So here, 1 plus 1 is 2, so I put down the 0 and I carry the 1. Now I've got 3, which looks like this. So I write the 1's digit, carry the 1. Again, I've got 1 plus 1 is 2. 2 looks like this. Put down the 0, carry the 1. This is a good one. And then 2, we got 2 again. Carry the 1, yay, no more carrying. And then this should be my result. This should be 50 if everything went well. Right? I'm just going to assume it is. We can check that. Is it?
Uh-huh.
Yes, thank you. Awesome. Beautiful. So, how does a computer do this? Let's think about the flow that's happening inside the machine first. So, inside the machine, there he is. There's barely a ledge here, so I'm going to probably lose this thing a lot. If anyone can find like a hot pink eraser for me, I will give you candy or something and pay for the eraser. Or something, yeah. So we want to add a couple of numbers. So I've got x plus y, and I give those to the computer. And these are in base 10. First thing it does is it converts to base 2. And in particular, it's going to convert to that very fancy format that we know of. And then inside, all the computer's got are switches. All it's got are ons and offs. But it also has logic. So the computer has very simple logic circuits built inside of it. And we're math folk. We're math and CS folks, some of us, but we're all math folk at our hearts. So let's just take a look at a couple basic logic gates. And the simplest one would be an AND gate. So I've got A, B, and then out. So these are going to be inputs. A and B are just either on or off. There's a signal coming in, or there's no signal coming in. Or maybe it's a negative signal, it's dropped. But we just think 1s and 0s are the input. And that looks like this. So this is an AND. And the way this works is the way logic works for math. False, false. You can think of 0 as false. You can think of 1 as true. False and false is false. False, excuse me, true and, I should have said and here. 1, 0 gives me 0. 0, 1 gives me 0. They both have to be true to get out of true. You learned this back in the logic and proof, right? This isn't very stunning. We also have OR gates. So an OR gate looks like this. It's a little sharper like that. And I've got A and B. So this AND gate is round. Looks like a Pac-Man laying on its side. And so here I have an OR gate. And the way this works is A, B, and then out. We need one of these to be on to get an out. So 0, 0 gives me nothing out, but anything else gives me something out. Gives me a true out. Whoop. Easy, buddy. And then there's one last one that I just want to point out here. It's called a NOT gate. So a NOT gate looks like this. And it just takes one input. It takes A and it turns out not A. So it flips it. If it's a 1, it goes to a 0. If it's a 0, it goes to a 1. So for this, if we have A, and then we have our out here. If A is 1, out is 0, 1. If A is 0, out is 1. If A is 1, out is 0. We're going to take these two and put them together into what's called a NOR gate. And a NOR gate is just this OR gate. God, I love this stuff so much. I wouldn't want to be a professor in it, but I do love it. Things always suck when there's pressure associated with them. So unless it's something you deeply, deeply love, it's part of who you are. So I've got an or and a not, and that's actually written like this. Put the little dot there, and then that's a NOR gate. So a NOR gate is this, and the outputs are flipped. So look at what we got here. We got A, B, and then out. And so when 0, 0 are the inputs, I actually output a 1. And then all the other outputs are going to be zeros. So whenever there's actually some sort of signal coming in, the output is 0. I think I need that. We'll find out in a second. So let's take a look at what's called a full adder. And this basically takes 2 binary digits and a carry that could have come in from a previous binary addition and puts out the result along with the carry. So a full adder looks like this. And I actually have to look at this to get it. So I've got an A comes in, a B comes in, and then this is the carry from some previous computation, so we'll call it carry in. And the first thing we do is, oh shit, I guess there's actually one more circuit I didn't show us here. Son of a gun. Okay, sorry. Last circuit. We need a XOR circuit. This is exclusive OR. This is what people think you mean as a mathematician saying OR. And the way this looks is A, B, and then there's a line, and then it looks like an OR. So that's like the exclusive part right there. We just call it XOR gate. This returns an out signal only when these are opposites of each other. So 0, 0, 1, 0 gives me a 1, 0, 1, 1. But 1, 1 actually is 0, so compare it to the OR signal, or the OR gate. Same thing, it's just they can't both be on. It's exclusively one or the other. So here, for the full adder, the first thing I do is I make these lines a little bit long. We're gonna put a XOR gate here, and sometimes it helps to just write them like that. And then this carry is gonna come across, and then over here, so we're gonna have an output that comes out, drops down. The carry is gonna ride along over to here, and we've got another XOR. And then we've got the sum actually comes out there. Remember, these A, B, and C in are only 1s and 0s, so true or false. And then I've got 2 AND gates down here, and these are going to help figure out our carry. And then these go together into, I'm going to connect things up into an OR, and then here's your carry out. And let's see here, so then we got to hook our wires up right. So from here, there's an attachment and an attachment, and these 2 wires come down and run into that AND. And I'll show you, this actually makes a lot of sense once we actually just start looking at it. And then this AND is connected to those 2 like that. There we go. Cool. All right, let's take a look. I guess I'm sorry I'm making you endure this. I freaking just love making these diagrams and chasing the 1s and 0s. So you're gonna have to suffer through it with me just a little bit. And at least it's semi-relevant to what we're doing. So let's see how this would work. Let's say I wanted to add 3 1s together. So let's say I had 1 plus 1, and then I had a carry 1 come in. So I carry 1, and then here's A, and here's B. What is the sum? Well, it should be 3 in base 2. So let's see if that works out. So the way to chase these down is to put a 1 and a 1 and a 1, and then roll through the circuit. So now look here. 1 and 1, XOR 1 is what? What does this guy output? 0. Exactly. So now I got a 0 there. Notice here I got a 1 and a 1 coming down. And that's automatically going to produce a carry on its own. Independent of what this is, 1 plus 1 is 0, carry 1. So I know I've got this 1 coming in right here. I don't know quite yet. Oh, that's an OR, so we already have a carry out, right? Because this is an OR gate. And we have one input that's on, so it's already going to be a 1. And then, where else do we got? So now we got to chase the rest of these wires. So here I had this 0 come out, so that 0 trickles down to here. And then what did we have here? This 1 was our carry that came in, and that goes here. 1 and 0 is 0. We have a 0 here. This doesn't change the result. But what do we have coming in here? We've got a 0, XOR 1, and that is a 1, because these are opposites of each other. They're not the same. So we get the result we expected. Add 1, so the 1 is the sum, and then we carry 1 over to the next column and add that in. You can chase this down. I actually put a little digital model of this in the content area under the binary stuff, so you can get in there, play with it, and just click the inputs, just, you know, if you don't have enough to do. All right, so I'll never quiz you on this stuff. This is just like good to have inside you. I think it's good to know these things from these machines that basically are extensions of ourselves now, right? We've all become bionic. We've evolved with these machines, so good to know what's happening. How about everybody grab a piece of paper? I'm gonna show you something cool now. Let's do something visceral. I got the paper for you. I got high quality, stolen paper. This is hot paper. Just be careful there. yeah. Good look. Oh, there's so many things I could do. It's true. All right. I want to show you a folding scheme. This is really cool. So you're going to actually learn two things here. And some of you have already seen this, some of you have done this, but it's fun, so why not see it again? So I would say about half the class has not seen this. So back in the 1970s, a Japanese mathematician, Fujimoto, came up with a type of computational origami, which is really cool. This has actually turned out to be something that is useful, just beyond how cool it is. Origami. So for example, origami is used to get solar sails, like when they work on the design of solar sails in outer space so you can harness the solar winds, you gotta have that solar sail folded up, and so they've used origami to find the most efficient folding and quickest unfolding of the solar sails. This isn't quite that cosmic, but it's still pretty freaking awesome. So Fujimoto came up with a way to fold an approximation of 1 over an odd number into the paper. So for example, well, if I wanted to fold this paper into an even multiple, it's no big deal, right? Like a half. We got this. A fourth. We got this. This is half's easy. Fourth is just do that twice. Eighth, do it 3 times. You happen to just think about binary for a second here. Just think about what I'm saying here. Just 1 fold for this, 2 folds for this, 3 folds for an eighth, 4 folds for a 16th, thinking about decimal places, our binary places. These are our places. And down the way. So in other words, here's a fourth, here's a half, here's a fourth, here's an eighth, Just keep that in your pocket. So Fujimoto said, well, how can we do this maybe to do a third? How could I fold a third perfectly into the paper? So there's a couple of ways to do this. One is the old, like when you fold a letter, and you just kind of, you tube it and try to get an approximate third out of the paper, or you just don't care, and then you just make a fold, and it's like, that's good enough. So Fujimoto said, start with the good enough. I'm gonna make an estimate of a third. So I fold this edge of the paper over and make a little crease here that looks like a fourth more than anything. So this is a third, but there's some error in it, right? It's a third plus error, and I don't know the error. But if this whole thing is 1 unit long, how much is here? How long is this side? If this is a third plus epsilon, how much is this? Because it needs to add up to 1.
2/3 plus epsilon.
2/3 minus epsilon, yeah. We want to make sure the epsilons cancel. Right, so whatever this error is here, if I overshot a third, I would have undershot 2/3 over here. And if this was an undershot of a third, this would be an overshoot. I'd actually be subtracting a negative. Key thing is just make sure that this plus this adds to 1. So over here, I've got 2/3 of something. Oh, I can do halves so easily. So I can take this right edge and fold it over to meet this and make a little crease right in the middle. And what I have now over here is a third. What's the error? It's half the error. So now I've just halved the error. Actually, so this estimate on this side, this is a better estimate of a third already by a factor of 2. I've halved my error. But then Fujimoto notes that if that's a third minus epsilon over 2, how long is this?
2/3 plus.
Epsilon over 2, indeed. And 2/3 I can cut in half by simply taking the left edge and folding it over to that previous crease. So when I cut this one in half, how long is that? A third plus epsilon over 4. I've cut my error in a quarter, in fourths. So this estimate is way better. Now let's just record what we did there. We made our initial fold, and then I did a right edge over, and then I did left edge over, and now I've got a new estimate, and I could repeat this if I wanted. If I want to make this estimate better, do it again, right? Take this as your initial estimate, do a right fold, bring the right edge over, bring the left edge over. If I do it again, what's my new error?
Is that a 6 plus epsilon over 18?
6, so factor of 4, so 16.
Ah.
Does that make sense?
Yeah.
Because it cuts the error in by 4. So if I do this again, then I've got a 16th of the original error. If I do it again, what would I get? What's 16 times 4? 64. Yeah, I was like, I wasn't quite sure. I was hoping somebody would tell me. 64. So if we just repeat this process over and over again, we get closer and closer to a third. Okay, let's remember that. Let's do a fifth really quick. Let's get some paper out and do this together. Grab that sheet of paper, my friends. Let's do a fifth. And I don't need to draw the whole rectangle. We can make our estimates just on a line because there's nothing vertical going on. Everything's horizontal. So take your piece of paper, make a bad estimate of a fifth of the way across, but don't crease the whole thing. Just make a little cinch at the top as to your estimate. So just pinch it at the top. And then now you have track of it. So let's say I did this really bad. It's a fifth, but boy, there's error on it. So I'm going to show you another way to think of this. I've got 1/5 approximately here, and then 4/5 approximately there. Does this make sense? This is approximately 1/5, and this is approximately 4/5 over here. I'm always going to fold even parts. So now I'm going to cut this piece in half. So take the right edge and bring it to your crease mark as good as best you can, and make another cinch. Kind of pull across and cinch right there. So what we've done now is we cut that 4/5 in half, and I've got 2/5 and 3/5. So right now, that little crease mark, this should be roughly 2/5, and this is 3/5. Every time we fold, we cut the error in half. But our whole estimate was for 1/5, so we got to keep going. I'm going to cut that again. So now, take that right edge again, and bring it to that last crease mark, and cinch. And what we've done is cut that in half. We should have 1/5 and 4/5. How much better is this right-hand estimate of 1/5 that we have now? Looks pretty good. Looks pretty good. In terms of epsilon, how many epsilons is it? If this was my original error, did 3 halvings, so it's an 1/8. So this is epsilon over 8 in terms of my error. Cut it in 8. But we're going to work back, because there's another even. We're going to work our way back to where we started. So now, friends, take the left edge and bring it to that crease on the right edge, the rightmost crease, and cinch at the top. And what you've got is a 2/5 and a 3/5. And what do you think we're going to do? We're gonna have that 2/5. So now bring them one last time. Boy, I've kind of like almost lost track of what I'm doing here. You guys are on it. I forgot where my folds were. I think it's this guy here. So cut that in half. Yeah, I think it's this guy. And now we're back to 1/5. So after we cut that in half, we should have a 1/5 estimate and a 4/5 estimate. Let's look at how many times we have the error. So here I have once, twice, 3 times, 4 times. So the new error is epsilon over 2 to the 4th, which is epsilon over 16. So we've got a 16 times better estimate than we had before of 1/5. And if your original estimate was pretty good, this could be just about perfect. But that's not what I really wanted to tell you. That's cool. That's what Fujimoto's like, this is cool, but there's more. Let's notice the folding pattern. So remember, we were doing 1/5. So we made our initialization of the process. We folded the right edge. We folded the right edge, and then we folded the right edge. And then the even appeared on the left. So then I folded the left edge, and then the left edge again. Sound right? See where I'm going? So now, here's how we're going to get a binary number out of that. I hate this eraser. I shouldn't hate it, because it's going to come back to bite me, probably. You're just fine, little eraser. So I'm going to record the folding pattern. So it was R, 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 L, L. Remember how, so this was the 5th. Remember what the 3rd was? It was R, L, and then that repeated. Same thing here. This also could repeat. And we could do this again, and then we'd have, how good would our estimate be if I took this as my initial guess and did this all again? 256. It would be 16 squared. It'd be a 256 times better estimate if I just simply did this again. So we're going to associate R with 1 and L with 0. Binary. And what we're going to do is read these things backwards. So this one was RRLL, so that's 1, 1, 1, 0, 0. Read it backwards and start with 0 here. So 0.00111. And if it repeated, it would be 00111, 00111 on down the way. I claim that is the binary representation of 1/5. Let's see. So 1/5 in base 10 is 0.2. Let's do the conversion. So we start with 0.2. Remember, for this, it's multiplying by 2. So I multiply by 2, I get 0.4. I multiply by 2, I get 0.8. So these are my first 2 digits of my binary expansion. Put that 0 there, put that 0 there. Multiply next by 2, you get 1.6. Record the 1, strip away the 1, and begin the multiplication process again. So times 2 is 1.2. Record the 1, get rid of it. Go back. Where am I at? Oh. Did I lose a 1? Did I count let's count my folds. Hey, could somebody go to World Class really quick and click on like a binary converter in the back? Let's just get this out.
Or with the 3 right folds, I think one of the arrows you're pointing to just another example you drew of the
Okay, thanks, Thomas. Did I? Okay, so let's see. So, oh shit, it is just 2 R's. Thank you, Thomas. Yeah, thank you. Yeah, I got a little too excited there. So it should have just been this, right? Yeah. So it's just 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and huzzah, that's actually what I'm getting here, because now I'm back to the beginning, so it repeats. So could you just really quick for me convert 1/7 into binary using folding paper? What is the binary expansion of 1/7 using this? I'll give you a few minutes. And remember, just kind of keep track of it. You can even just do it on paper if you want. Because 1/7 is going to start like this. You've got a 1 and a 6. You can kind of just keep track that way. But it's fun to get nice and visceral. And I'll look it up, make sure we get it right. Remember, you always fold the even part. Yes, that's okay. You don't have to go too far on this, right? You actually end back up. You want to end up back where you started. You work this until you have a 1 on the left, one part and 6 parts on the right. Check it out. Make sure you see that. I'm gonna actually, I don't know what 1/7 is. It's like, there's a 14 and a 28. Oh, do you know it? No. It's I know a magic trick based on 1/7 decimal representation. It's not a very good magic trick. It's kind of like super nerd magic trick. Okay, so, oh yeah. 14, 28, 57. So 1/7. 57 or 56? 57. And then that repeats like that. And so let me convert that over to binary. So I'm just taking that decimal and I'm going to enter it into one of the binary converters I gave you all. Let's see, how do I even start this? This just seems like too much. I'm not doing that. So we'll just do it and imagine 14, 57. And you want to add quite a bit. You don't want to do just one repetition. I would do at least 2 of the repeating decimals. And we're right. So I just checked it out. That's totally a 7. I'm going to point out one more thing here. That this number for a 7, there's some cool Calc 2 stuff hiding here. Because this goes on like this. So keep in mind that this is 2 to the -1st, 2nd, 3rd. This is 2 to the -6th. This is 2 to the -9th. 2 to the -12th. So 1/7 is actually 2 to the -3rd, plus 2 to the -6th, plus 2 to the -9th, 2 to the -12th, on down. So it's this fraction. How do I add this sum up? If I just gave you this sum, this infinite sum, how would you add it up?
0 to infinity of 1/2 to the n plus 3.
Oh, I like that. Oh, I love that's a beautiful, yeah. Cormac is giving us the lovely series representation. So let's see, so 3k, k equals 1 to infinity. A beautiful, beautiful representation. What kind of series is that? It's a geometric series, beautiful. It's a geometric series. So this is geometric. And when we have a geometric series that looks like this, something like that, and we could have an A in front. This is equal to the first term over 1 minus the common ratio. If the series converges, and what is the condition for the series to converge?
If it goes to 0. Or if it,
The terms definitely have to go to 0. If they don't go to 0, it doesn't converge, absolutely. But for a geometric series, what has to be true about that ratio?
it's less than 1.
Less than 1. And here, our ratio is actually 1 over 8 to the k, because that's 2 cubed. Our first term here is 1/8, so this adds up to 1/8 over 1 minus the common ratio. Am I getting a 7th? Yeah, I am. Check it out. So this is 1/8 over 7/8. 1/7, so we know we got it right. Just trying to remind you that other math has been had by you all. Other math will fit into this class at some point. Today was just kind of a little bit of fun. So we can call it today. How about that? That's a good place to end. Nobody's ready for any more. First week's always hell. I'll hang out here if you want to work. If not, how about we make this This is a classic thing of mine too, isn't it? How about we make this homework due next Friday so you can ask questions on Wednesday? I had forgot about the Monday. And even if I hadn't, I do this all the time anyway. So next Friday, the written homework is due. Don't forget about the Python primer. Whether you know Python or not, I want to see you knock that out. I'll knock it out with you. And I'll see y'all on Wednesday. Yeah, Wednesday. I'm in my office from 1, actually after this class till 2 today, and then Friday 1 to 2, if you need anything. And if you can't make those, let me know, we'll figure it out.